So welcome everyone to today's seminar. Today it's a pleasure to introduce Bruno Rodriguez del Pino, who is currently a permanent researcher at the Centro de Astrobiología in Madrid, in Spain. Bruno obtained his PhD at the University of Nottingham and then moved to CAB to work in preparation for the observations of NIRSpec, the NIRSpec instrument of the James Webb Space Telescope as part of the GTOT. He has been part of the NIRSpec commissioning team and has participated in the commissioning of the instrument during the 6 months after launch. So now Bruno is working on the study of the interstellar medium and gas kinematics in high Z star-forming galaxies. So Bruno, thank you very much for accepting our invitation. When you're ready, the floor is yours.
Okay, great. Thanks a lot, Anna, for giving me the opportunity to share with you the work that we are obtaining with the James Webb, and in particular with the GA-NIFS survey. So today I will be presenting part of the results that we are obtaining within this GA-NIFS NIRSpec GTO survey. And I will focus on the study of the spatially resolved properties of a galaxy redshift 3.7, in which we have been able to study the interstellar medium and the kinematics. So here is a list of the people that are part of the GA-NIFS team. The PIs are Santiago Arribas and Roberto Maiorino, and the program leads are currently Anna Ubler and Michele Perna. As you can see, we are like a big group of people that are trying to exploit all the amazing data that we are getting from the James Webb. So this is an outline of the talk. I will start with a brief introduction about what we knew about the high redshift universe before the arrival of the James Webb, and I will describe the capabilities of this instrument, in particular to study the high redshift universe. I will describe our collaboration, the GA-NIFS, that stands for Galaxy Assembly with NIRSpec, Integral Field Spectroscopic, and I will show you some of the fresh results. And I will then go into the details of the study that I have led on the properties of a galaxy group at redshift 3.7. So to start with, I show you this diagram that displays like some of the major milestones of the evolution of the universe during the 13.8 billion years after the Big Bang. So around the 400,000 first years, the universe was mostly neutral. And it wasn't until the formation of the first stars that the hydrogen in the intergalactic medium and the circumgalactic medium started to become ionized, starting what we know as the epoch of ionization that lasted several hundred million years until the universe became fully ionized. And since then, galaxies continued their evolution, assembling their mass, evolving chemically until they became the evolved galaxies that we see in the local universe. So far, we have been able to study in detail the universe at redshift between 2 and 3, thanks to the possibility to access the optical rest frame emission lines. And this has been possible thanks to both space-based and ground-based facilities that have access to the near infrared regime up to around 2.5 microns, such as HST and ground-based telescopes such like Subaru, Keck, and VLT. And also with a Spitzer, we could go up to 4.6 microns. And then with ARMA, we have been able to trace also the far infrared emission in very high redshift galaxies, like beyond redshift 2 and 3. And also we have been able to study these galaxies through the ultraviolet regime. However, at this very high redshift, we have very little information about a handful of objects because we can only target the very bright galaxies. So what we knew, some of the things that we knew about the universe at early stages was that at around redshift between 1.5 and 3, there was an epoch dominated by star formation, by intense star formation, as you can see here in this diagram, showing the star formation rate density as a function of redshift. And you can see that at around 3.5 gigayears after the Big Bang, at around redshift 2 or so, there was like a peak in the star formation rate density of the universe. And we have been able to study galaxies in detail, in particular massive galaxies like the one I show in the right panel, with especially resolved observations. Okay, so this is a galaxy at redshift 2.4 more or less, and this is like a very high star forming galaxy with high stellar mass, and thanks to instruments such as Symphony, we have been able to resolve its properties such as the star formation rates as highlighted in this map. If we integrate at each single epoch the star formation rate density that we have in the left plot, then we get this plot on the right that shows the stellar mass density. So it's the amount of stellar mass that was formed at each epoch. And as you can see, at around the same epoch, at 3.5 gigayears after the Big Bang, already 25% of today's stellar mass density was already in place. So galaxies already assembled a significant amount of their stellar mass. However, not only the star formation rate was peaking in this epoch, also the growth of supermassive black holes was also very intense. As you can see in this diagram that shows the black hole accretion rate density as a function of redshift. Here in gray, you can see the star formation rate density, so the same plot that I showed you before, and the other lines represent the rate of growth of supermassive black holes at different epochs. And as you can see also between redshift 2 and 3, there was a peak of intense black hole growth. So this is telling us that before this epoch, galaxies are expected to be assembling a significant amount of the stellar mass through different processes, such as the star formation of the accretion of gas and stars via inflows or mergers. And at the same time, all these processes are favoring the growth of the supermassive black holes at their centers. It's important to bear in mind that these intense processes, star formation and AGN activity, have an impact on their host galaxies, which we call feedback processes, that can take the form of, for example, galactic outflows that can influence the evolution of as I said, of the host galaxy. For example, feedback from star formation, in particular coming from supernovae and from AGN activity, are needed in simulations, like in theoretical models, in order to predict the observed fraction of galaxies at low and high masses. So we can see in the left plot, we can see that we need, so the pink line shows the model predictions, and the black dots the observations, and we can see that at low stellar masses, we need feedback from supernovae in order to reduce the number of, like the number density of low mass galaxies that the models predict, and at high masses, we need the feedback from AGNs to predict, like to decrease the growth of the most massive galaxies. So models predict the presence of these feedback events, and this is something that we are continuously trying to search for in observations. Here I show an example of a galaxy at redshift 2.4. This is a galaxy hosting a quasar, in which we can see that the distribution of the star formation that's shown here in this color-coded map through the H-alpha emission presents like a hole the center, which corresponds to the region where the quasar is launching a powerful outflow that is, in this case, highlighted by the white contours. So in this case, this galaxy seems to be quenching or suppressing star formation due to the action of the galactic outflow. Another consequence of the feedback from star formation and alien activity is related to a global relation that is quite well known between the gas metallicity and the stellar mass. I show here an example of this relation at redshifts of 2.3 and 3.3. And in principle, this relation could be thought to be held because more massive galaxies, they form more stars, and therefore they will have like more metal-rich gas because they will enrich more the interstellar medium through more intense star formation. But it's not only that. Most massive galaxies are also more efficient at keeping their metal-rich gas. Okay, so in this diagram that I show here, comparing the metal loading factor, which is the rate at which galaxies expel their metal-rich gas, as a function of stellar mass, we can see that at lower stellar masses, this metal loading factor is high, whereas it decreases very deeply with mass. Okay, so at high stellar masses, it's very difficult for galaxies to expel their high metallicity gas. And this contributes to maintaining the mass metallicity relation. So in order to observe this high redshift universe and try to study these properties that I have shown you for galaxies below redshift 3 or 4, we need to target the optical rest frame emission lines. Okay. So this has been difficult until now because we didn't have instrumentation that could go beyond 2.5 microns in ground-based and space-based telescopes. For example, in the spectrum that I show you here of a galaxy at redshift 3.4, we could only reach the oxygen 3 line at 5,000 angstroms. Beyond that, we cannot, for example, the H-alpha line was not accessible until now because it goes beyond the 2.5 microns in the observed rest frame. So we need to go beyond this limit, and we also need to have like more sensitive instrumentation and the possibility to study the detailed properties of these galaxies, because most of the studies so far of high redshift galaxies have been focused on the integrated properties of galaxies. And on top of that, we have needed to stack several spectra of galaxies in order to have enough signal to noise to characterize their properties. So in order to explore the high redshift universe above redshift 2 or 3 and even beyond redshift 10, we really require a powerful infrared telescope that goes beyond 2.5 microns that should be capable of resolving the internal properties of distant galaxies. So in this sense, we are very lucky because more than 2 years ago, in December 2021, the James Webb was launched. It started the operations in summer 2022. So we have already almost 2 years of scientific operations of this telescope. As you probably know, this telescope is placed at the Lagrange point 2, so it's at 1.5 million kilometers away from Earth, so much farther away than Hubble, because it needs to be working at very low temperatures. One of the main differences with respect to the Hubble Space Telescope is the size of the primary mirror that you can see here on the right. It has a primary mirror of 6.5 meters, which is more than 2 times or almost 3 times larger than the one of the HST. And the other important thing is that with the James Webb, as you can see in the bottom, we can cover from the near infrared from 0.6 microns up to 28.5 microns, deep into the mid-infrared regime. So we can really cover a wide range of the infrared regime to study the emission of the very distant galaxies. Here on the left, I show you the comparison in the fluxes that can be detected with the NIRSpec, with the James Webb instrumentation, shown in red, in comparison with the other instrumentation that was available before, okay, ground-based and space-based. And as you can see, we can detect fluxes that are between 10 and 100 times fainter than we could before. So we are really making a big step in sensitivity with the James Webb. And the other important thing is that not only the James Webb is more sensitive, but it also has instrumentation that it wasn't available before on space. In particular, that one instrument mode that is available that I will focus on the talk is the Integral Field Spectroscopy, which allows to obtain within a small field of view between, in the case of the James Webb, between 3 × 3 arc seconds up to around 8 by 8 arc seconds squared, like hundreds of spectra of individual regions of a single galaxy, as shown here. So this provides like a very powerful tool to study the internal properties and also the close environment of our galaxies. And this is a mode that is available in the near infrared with the NIRSpec instrument and in the mid infrared with the MIRI instrument. So with the James Webb, we will be able to go much farther than we were able to go before with the previous instrumentation, deep into the epoch of radionization and beyond. So as you probably know, we are already detecting galaxies beyond redshift 13, and probably in the near future there will be like more newer detections of even more distant galaxies. So I will now describe our collaboration, the GA-NIFS survey. So as I said before, this is a NIRSpec GTO survey. So in total, in cycle 1 and 2, we had around 260 hours, and now we have in cycle 3 additional 70 hours. And we have built a sample of more than 50 large and bright galaxies from redshift 2 to redshift 11. And these are galaxies from a wide variety of classes. We have star-forming galaxies, galaxies with an active galactic nuclei, dusty star-forming galaxies, quasars. And these were selected to be, as I said, bright and large in order to exploit the full capabilities of the integral field spectroscopy, because we can really study the whole galaxy in detail. Here I show a summary histogram of the distribution of redshifts that we have for our sample. As you can see, we reach up to redshift 11 or 10.4. No, this is the GNC 11 galaxy that you probably have heard of. As you can see, we have a wide coverage of the first giga years of the universe. And the main goals of our program are to study the internal properties and the close environment of all our galaxies, aiming at unveiling what are the physical processes that are driving galaxy evolution in the first giga years of the universe. For example, we want to understand what are the processes through which galaxies assemble their stellar masses, how they have enriched their stellar populations and their interstellar medium. What are the roles played by AGN and stellar feedback? And also whether environmental effects might be already at place at these early epochs. For that, we are observing our galaxies in the high-resolution mode of NIRSpec, targeting the main optical emission lines. Here you can see for the different redshift beams that we have, what is the main optical lines that we cover. Okay, so for example, for the galaxies at redshift between 3 and 4, like the one I will show you later, we cover from oxygen 2 to sulfur 2 lines. Whereas whereas H alpha is detected only until redshift 7, and then beyond that, beyond redshift 7, we can only target like oxygen 3, H beta, etc. Okay, to lower wavelengths. And we also have observed all our star-forming galaxies with the R100 spectral resolution in order to constrain the properties of the stellar population through the study of the continuum from 0.6 to 5.4 microns. So I will show you now some of the first results that we have obtained. This is I just want to highlight some of the results from my colleagues. I will be very brief, just to, in case you are interested in some of them, I invite you to go and check out the paper because they are already in press. So the first one was led by Michele Pernar on the study of this originally candidate to be a dual AGN, a redshift 3.3. And he found that, he confirmed the fact that there is next to the quasar, there is an AGN that he labeled GIL. And not only that, but this environment contains at least another 9 companions that were detected by the oxygen-3 emission. So telling us that this is like a very overdense region. Apart from that, from the study of the AGN, Michele developed an algorithm to remove some instrumental signatures that appear in point-like in observations of point-like sources due to the undersampling of the NIRSpec PSF. So as you can see here in the bottom right, the data presents some wiggles due to this undersampling that has to be modeled and removed in order to work with the data. So this software has been prepared by Michele and can be used by the community. Also related to dual AGN, Michele, also in this other paper, he identified a high fraction of AGN that presented a companion that was also an AGN. So within a total of 17 AGN systems that we have in our survey, he identified 5 cases of AGN pairs. And as you can see in the diagram here, the results from simulations, these fractions are significantly higher than expected in simulations. So this is informing simulations that this occurrence of dual AGN is higher than originally expected. In relation also to quasars, in this work by Madeleine Marshall, she studied 2 of the highest redshift quasars known to date, and she was able to constrain the masses of the supermassive black holes at the centers through H alpha and through H beta. And she could also study the host of these quasars by subtracting the emission from the quasar itself. And this is shown in the right panels, where you can see and this is the oxygen-3 flux of the host galaxies, and you can see that in both cases the host galaxy presents companions. So this system seem to be merger candidates. In this other work by Gareth Jones, he studied this massive starburst galaxy at 6.3, where that is a lens system, where he was able to identify several pairs of galaxies lying at very close redshifts. And he also found that there isn't only one starburst galaxy, but there seems to be like more than one system that is undergoing starburst activity. Another submillimeter galaxy is this one that was studied by Eleonora Parlanti, where she found, we knew that this galaxy was an AGN, a type 2 originally, but she also found in the very nucleus of this galaxy the presence of a broad line region with a huge full width at a half maximum, and on top of that, a high velocity outflow. So this was a galaxy that, as shown in the bottom panel on the left, on your right, no, on your left, sorry. The C plus emission showed that a very like a stable disk with low velocity dispersion, shown by the blue dots, but the H alpha emission that we can trace with NIRSpec shows like a much higher velocity dispersion. So despite the outflow seems to be not having a strong impact on the star formation activity of the galaxy, because the mass loading factor is only around 6%, it seems to be having an impact on the gas, on the kinematics of the gas. Therefore, this might be the moment at which the agent activity is starting to have an impact on the host galaxy. And just the last result that I wanted to show you is this work led by Santiago Arribas, here also at CAB, where he studied one of the most massive dusty star-forming galaxies at high redshift, a redshift almost 7, where there is a system that is composed by 2 dusty star-forming galaxies. So it was already known to be a very massive system, but he has found a total of additional 10 more galaxies in the system, as shown in these maps. So this was based on submillimeter observations. It was a candidate to be an overdensity or a protocluster. So these observations with NIRSpec are confirming that this is a protocluster and is like a very massive protocluster that is probably evolving into a coma-like cluster in the local universe. So after briefly presenting these results, I will now move into the work that I have led on the study of this galaxy group, a redshift 3.7, which is the one I show here on the left. For this galaxy was already known to have high star formation rates, around 50 solar masses per year, and a stellar mass of 10 to the 10 solar masses. And we observe it with the standard configuration that I described before, with a high resolution, targeting from oxygen 2 to the sulfur 2 lines, and also in the R100 mode with a total of 1 hour. As you can see, this is a system that is composed by 3 galaxies. We have the main one that is GS4891, the northern component that I have labeled with the _N, and then this companion on the east that is 28356. Here I show you the integrated spectra of these 3 galaxies. As you can see, in the main galaxy of the system, GS4891, presents like very high signal to noise, like with a plethora of emission lines, with high signal to noise in the oxygen 2, oxygen 3, H alpha, and H beta. So really providing us the possibility to constrain, to really study in detail the interstellar medium. And then the other 2 galaxies present lower signal to noise, but still enough lines to study them in detail. Here I showed some maps of the emission line fluxes from oxygen 2, oxygen 3, and H alpha, and as you can see, especially in oxygen 3 and H alpha, which are the brightest lines, there is like a lot of extended emission in this system. Even there seems to be like a connection between the main galaxy and the northern component. And if we look in detail on the main galaxy, and I'm looking now at the bottom left, you can see some substructure, some stellar clumps that we have identified very close to the oxygen 3 emission. And these are, we have labeled them like C1 and C2 because as we consider them as star-forming clumps based on the flux in oxygen 3 and H alpha. So these observations confirm that these 3 galaxies are part of a group lying at a very similar redshift, okay, a redshift 3.7. We integrated the H alpha star formation, the star formation rates from H alpha. For the main system, we have like 37 solar masses per year. In the northern component, around 14, and in the other one, much lower star formation rates. And if we compare this with previous estimates from HST, that in particular, the ones that took into account the emission from the main galaxy and the northern component, we can see that they are very similar. So the ones that were obtained from SED fitting using HST and Spitzer data are very similar to the ones that we can trace from the H alpha emission. And on the right, I show the distribution of this star formation rate activity, where we can see that it peaks at the center of the main galaxy and also at the center of the northern component. I will move now into the analysis of the properties of the interstellar medium, starting with the nebular attenuation, which is something that we can constrain quite well because we have several Balmer emission lines from H delta to H alpha. So we start by estimating the nebular attenuation from the Balmer decrement, the ratio between H alpha and H beta, and this is the map for the whole system. In this case, we had to bin the data in order to boost the signal to noise in the H beta line that is needed to estimate this nebular extinction. And as you can see, this AV value is quite heterogeneous throughout our system, although there are like some characteristics that stand out. For example, between the main galaxy and the northern component, there is the highest extinction of around 2 magnitudes, and these two stellar clumps, C1 and C2, present the lowest extinction that are almost negligible. Thanks to the access to this series of Balmer lines, we can also compare the attenuation in our galaxy with the attenuation loss at low redshift. Here I show the values that we get assuming both standard attenuation loss that are used in the local studies, the Cardelli and the Calcetti ones. And here I show the AV values that we get for the different ratios of the Balmer lines. And as you can see, in all cases, they are consistent within the errors. So this is telling us that the attenuation in our system is consistent with those of local galaxies. Another important property of the gas that we can study, thanks to the access to so many optical emission lines, is the gas metallicity or the oxygen abundance. So this is here I show a list of indicators that are used to constrain the metallicity of the gas, depending on the lines that we can access. In particular, they use the oxygen 2 line, the oxygen 3 and H beta, and also the H alpha and the nitrogen 2 lines. On the right, I show that 2 of the papers that have produced calibrations based on these indicators to obtain the oxygen abundance. Okay, so in the left, I show the recent work by Sanders using James Webb data of galaxies between redshift 2 and 9. And on the right, I show the work by Curti of local galaxies. Okay, so in principle, one would say that we should use for our galaxy those by Sanders that are at higher redshift. But as you can see, as you will see in the next slide, the regime that we prove of metallicity is relatively high, so between 0.3 and 0.6 solar metallicity. And at this regime, the calibrations by Sanders are not so robust, whereas the calibrations by Curti for the local galaxies provide like a much better constraint of the relation between these indicators and the oxygen abundance. Thus, we use these indicators based on local galaxies, in particular the ones that I highlight there, R2, R3, R23, and O32, which are using the oxygen 2, H beta, and oxygen 3 lines. And here I show on the left the distribution of the gas metallicity. That, as you can see, it ranges from 0.35 to 0.6 solar metallicity. And there are like some things that stand out as we look at the distribution of the gas metallicity. The first one is that there is a clear gradient from the south of the main system to the northwest of more than 0.4 dex. And also the northern component presents, even though it is less massive, it has like a stellar mass around 5 times lower than the main galaxy. It presents metallicities that are up to 0.2 dex higher than at the center of the main galaxy. So if we look at in detail at these 2 results, first looking at this metallicity gradient in the main galaxy from the bottom to the north, from the south to the northwest, but also from the center to the northwest. So from the center to the northwest, there is like around 0.2 dex or higher difference. Okay. This lower value that we see in the south might be due to the presence of this star-forming clamp that might be related to a minor merger or perhaps an inflow of low metallicity gas. But this drop in metallicity at the center compared to the northwest is similar to other gradients that have been found in the literature of a slightly lower redshift galaxies, like a redshift 3.2 and redshift 1.5 in these works by Cressy and Curti. And they associated this drop in metallicity in the center of galaxies to the possibility that these galaxies are accreting low metallicity gas via an inflow that is producing this drop in metallicity at the center compared to the outer regions where the inflow is not reaching. The other result that we found is this higher metallicities in the northern component. And this is in contrast with what I showed you at the beginning, this mass metallicity relation in which most massive galaxies tend to have higher metallicity. In this case, we see the opposite. No, the less massive galaxy has higher metallicity. And this is telling us that perhaps one of the possibilities that could be happening in this system is that there is the most massive galaxy is due to its stronger gravitational potential, accretes more easily gas from the circumgalactic medium. So this low metallicity gas could lower the metallicity in the main system and keep the less massive system with its higher metallicities. So this is one of the possibilities. And if it is true, it will imply that we are already witnessing environmental effects at this high redshift. Another property of the interstellar medium that we can constrain thanks to the wide optical regime that we cover with our observations is the electron density of the gas. This can be done both with the oxygen 2 lines and the sulfur 2 lines that are at the edges of our spectra. Using the ratio between these 2 lines that are both doublets, we can constrain the electron densities. In our case, we have to use the integrated emission from the main galaxy because the signal to noise in the sulfur 2 lines is quite low, as you can see here. And also we have to bear in mind that at the spectral resolution that we have in our observations, the oxygen 2 doublet is not resolved. So here the 2 lines are blended. So the modeling of these emission lines is challenging. It's not easy, but at least we can provide an estimate of the electron densities that we have in this system. So from the modeling of both doublets of emission lines simultaneously to provide both of them the same solution of the electron density, we get an electron density that is quite high, that is around 770 particles per cube centimeter. So this result, this very high electron density is compatible with an increase with redshift. Comparing with observations from a local universe, we have electron densities of around a few tens, whereas at redshift 2.3, this electron density has increased up to a few hundreds, between 200 and 300. But this value that we are getting is even higher. No, it's more than double the previous estimation. So this is like a huge increase in just in a small time, no, like in a small redshift window. If we compare it with these other galaxies at redshift between 2.7 and 6.3 in this work by Reddy and collaborators, we can see that so in this plot the electron density decreases to the bottom, okay, and we can see that the stellar masses of our system of around 10 to the 10, the galaxies tend to have lower electron densities than what we measure in our system. So something is making this galaxy a bit different to the rest of the massive population. We have to bear in mind, of course, that the errors in these estimates are large, but so they are the ones from previous works. Also, we explored the excitation mechanisms through our system. This is can be done thanks to diagnostic diagrams that are generally used also in the local universe. This is the BPT diagnostic diagram that uses the ratio between the oxygen-3 and H beta line on the y-axis, and the ratio between the nitrogen-2 and H-alpha lines in the x-axis. And depending on where the points land in this diagram, they will be compatible with ionization coming from star formation if they are in the bottom left, or for example with AGN activity if they are more towards the top of the diagram. What I show in the gray contours are the galaxies from the Sloan digital sky survey at low redshifts. These two lines, the dash and the dotted lines, separate this star formation and AGN regime. In principle, if we look at the distribution of the star-forming galaxies in the local universe, our galaxies that are represented here by red dots will look like they are above the star-forming population, like moving closer to the AGN regime. But if we compare it with the location of the star-forming galaxies at redshift 2.3 by using this work by Strom and collaborators, we can see that they lie very close to that. So our galaxies will be compatible in principle with star formation, but of course the conditions have changed from local redshift to high redshift. So that's why they are located in a different region of the diagram compared to the local galaxies. Here we have also to note that perhaps, I mean, probably you have read it in several papers that the classification of galaxies at high redshift is becoming more challenging with these kind of diagnostic diagrams, because at low metallicity, AGN tend to move closer to the star-forming regime in this diagram. So for example, I'm showing here those two AGN by green stars, which are two AGN that we have studied actually in our survey, and these are clear AGN because they show, for example, broadline regions. However, the line ratios place them very close to the star-forming regime. So these galaxies, in principle, would not be possible to classify them through this diagnostic diagram, because they have around like low metallicities. In this case, it's around 0.2 solar. However, in our case, as I showed before, we have metallicities between 0.35 and 0.6 solar, so quite relatively higher metallicities. So at these regimes, this BPT diagnostic diagram should still be reliable to classify the excitation mechanisms. So we can conclude that our galaxy, our system is consistent with star formation activity. And just I will move on the final part of the talk, just presenting the results from the study of the gas kinematics. In particular, we're using the oxygen-3 and H-alpha emission lines, which are the strongest. Here I show the velocity and the velocity dispersion maps. For the velocity dispersion, instead of the sigma, I'm using this WAT value, which is a non-parametric estimate of the velocity dispersion. That is the difference between the velocity at the 19th percentile and the velocity at the 10th percentile. Okay. So as you can see, the main galaxy highlighted here with an orange ellipse displays a rotation pattern that could indicate, like a velocity gradient that could indicate rotation. The northern component also displays a gradient in velocity, but is less compatible with the possibility of rotation. I will show in the next slide what we obtained from the modeling. And then looking at the velocity dispersion map, we can see that between the northern component and the main galaxy, there isn't like an increase in the velocity dispersion. So in principle, this will not be consistent with an ongoing merger. So perhaps these two systems are in a pre-merger stage. And also we can see that in the main body of the galaxy, the velocity dispersion is quite flat, and it increases towards the northwest of the system. Okay, with values above 300 kilometers per second. from the modeling of this velocity gradient in the main body of the galaxy, we obtain that this galaxy is consistent with the existence of a rotating disk. And from this analysis, we get a dynamical mass of around 1.7 10 to the 10 solar masses, which is about 3 times larger than the stellar mass that we obtained within the same aperture. So in principle, this galaxy would be consistent with being dominated by dark matter. Through the analysis of the emission lines, we identified the presence of an additional, the presence of asymmetries in the profiles of the lines, and in particular, motivated by this finding of the high velocity dispersion in the northwest, we identified the presence of an outflow in individual spaxels and also in the integrating this region on the northwest. Here I show the modeling of some of the stronger emission lines, where you can see that there is a clear blue shifted component in the integrated spectrum, and the fact that we can detect it in several emission lines allow us also to constrain the properties of this outflowing gas. These properties are shown here in the table on the bottom right, so we estimate a size of the outflow of around 1.5 kiloparsecs. The sigma, the velocity dispersion of the outflow, reaches up to 200 kilometers per second, with an extinction of around 1 magnitude. And here we find out that the metallicity is quite high. So we find an oxygen abundance of 8.5. Sorry, I forgot about this. So we can place it also on the BPT diagram, and we can see that it's consistent with also with the star formation activity. So it's driven by star formation. And coming back to the metallicity measurement, we can see that this value is around 0.2x larger than what we have at the center of the galaxy, okay, where we have around 8.3. So the fact that we find that the outflowing gas is more metal-rich, and it is, I mean, of course, we have projection effects, but the fact that it seems to be aligned with the gradient in metallicity that we observe, it might indicate that this outflow is redistributing the gas throughout the galaxy and potentially creating this metallicity gradient. In relation to the outflow, the outflows in the local universe, at least, have been associated to an increase in the electron density of the interstellar medium. So perhaps the presence of this outflow around the nuclear parts of this galaxy are also leading to an increase in the electron density of the gas, and that would contribute to explain why, for this system, we obtain so high electron densities. So just to finish, I would like just to summarize what I have told you. I have presented results from the GA-NIFS program, which provides IFS data with the NIRSpec instrument aboard the James Webb Space Telescope at low and high resolution. And we have a sample of more than 50 galaxies between redshift 2 and 11. Our main goal is to unveil the physical processes that are driving galaxy evolution in the first giga-years of the universe. And we have already several works published studying the properties and impact of AGN, the quasars and their hosts, and the environment, the properties of dust transforming galaxies, and the possibility that they are the protocluster sheets. And also, as I showed you in this work, the regulation of metals and the impact of outflows in star-forming galaxies. So in particular, for this one, we identified this star formation-driven outflow towards the nucleus of this galaxy that could be explaining this metallicity gradient that could also be due to the inflow of low metallicity gas. So both processes perhaps might be contributing to the generation of this metallicity gradient. I think I will leave it there. So I will be happy to take any questions. Thank you.
Thank you, Bruno. Do we have questions? Microphone. So whoever has questions, just can come closer because the microphone is here. Não subir muito, porque a câmera também.
Well, thanks for your talk. Very interesting. I wonder why you didn't consider the excitation by shock, because you have a very high star formation and also you have outflows. And probably if you use the diagnostic diagrams only considering the star formation, probably you will get problems with the metallicity and also with the density.
Well, yes, thanks for that comment. It's true that our system could be consistent with shocks. Unfortunately, we don't have, so if we plot the models of the ionization from shocks in this BPT, probably they will lie, our points will lie on top of those models. No? So perhaps they can also be explained by that. However, we don't have like other strong emission lines such as the oxygen one that is very, like, is more helpful to constrain the shocks. But I agree. I mean, I agree that shocks might be also relevant here. I don't know how much they could impact the estimation of the gas metallicities. If they could explain the differences that we see.
Your sulfur line are very bright, and when you have a shock, the consequence is the very bright sulfur lines. So you can use those lines for determination of density, because the problem is the shock, the excitation.
Yes, so in principle, we use the SAFOR 2 lines to estimate the density. We cannot, as I show you, where is it? Yes, here. So I mean, the SAFOR 2 lines are quite noisy, so we cannot really constrain very well the electron density, but and we cannot really spatially resolve the electron density to see if the regions that are not co-spatial with the outflow might have different densities. But for sure, yes, I agree that the shocks might be playing a role.
Okay, thank you.
Thank you.
Do we have more questions, either from the audience or Zoom? Thaisa? Stay around here, that you are here. Okay.
Hi, thanks for the presentation. I probably missed in the beginning. How did you select the sample? These 50 galaxies, are they selected by what?
Well, by a variety of reasons. Let me go back here, one more or less here. Yes. So the star-forming galaxies were selected in principle to be like on top of the main sequence at the redshifts and to be very extended. For the AGN, I think I'm not sure, but I think we applied a cut in luminosity. But I'm not sure for the AGN sample. And the other ones, the very high redshift galaxies, we wanted to select the highest redshift quasars, and also like these dusty star-forming galaxies that are very extended. They were like the ideal sources to study with the IFU. So the idea was also to showcase the capabilities of the IFS mode of NIRSpec.
Okay. I would like to understand the last work that you did. So you found a metallicity gradient. The highest metallicities were outside the main body of the galaxy, were in the two clumps to the north, west, east, northeast. Is that expected? Because I would expect that maybe you would have more metallicity in the biggest clump, or I don't know, the larger clump.
Exactly. Yes, that is what I was trying to explain before. That in principle we will expect lower metallicity in the northern companion.
Yeah.
So one of the ways that we have found to explain it is that the most massive galaxy is more favored to accrete the low metallicity gas from the circumgalactic medium because of the stronger gravitational potential, and that is producing like this environmental effect. Like the least massive galaxies will be less favored to accrete low metallicity gas, and they will maintain the higher metallicities.
Okay, another aspect I think it's important also is that the DPT diagrams that we know and use are usually were built for the present day universe, right? So I think there is maybe degeneracy between, the excitation and metallicity. So,
There
so
is.
that's, yeah, so those clumps to the north, I don't know, because in the excitation, you classify them as like not exactly star forming, but not AGN, intermediate or a mixture of composite, maybe, yeah.
Yeah. So based on the local galaxies, they will lie in this intermediate regime. But if we look at the star-forming galaxies at high redshift, they will lie as shown here by the cyan line. Basically, they will be consistent with also with this star formation. The problem with the low metallicity AGN is that they move to the star-forming regime. The star-forming galaxies don't move to the AGN. No, so if we find something in the AGN, is for sure they are AGN. The problem is that
I agree. Yeah, when you have a very low metallicity AGN, they would move towards the star-forming region.
Exactly. So I mean, in our case, because we have relatively high metallicities, we think that the classification is robust. But of course, if we had another tracers like in the UV or other emission lines such as the helium-2 that we don't detect in our galaxy, we could constrain better whether it is an AGN or not. But in principle, we don't have evidence that it could be an AGN.
Okay, thank you. Just a last question. You would expect this kind of metallicity at redshift 3.7, or you think it's high metallicity or too high?
Well, if we compare it, I have the slide that perhaps can explain this better. So this is the mass metallicity relation at redshift 3.3. So you can see that there is a lot of scatter, but so in the different circles of different colors, I show the values that we get in our galaxy. So the metallicity at the highest metallicity will be consistent.
It's consistent. Okay. Okay. Thank you very much.
Thanks, Bruno. We have one more question.
Yeah, it's a very quick question. Maybe I missed. But what are the stellar masses of these galaxies in this group?
So I don't remember the one of the lowest of the companion on the east, but the main one is around 10 times 10 to the in log mass is 10.1, and the northern component is 5 times less massive.
So 10 to the 10, more or less.
Yes.
Okay. Thanks.
Do we have more questions from Zoom? No? More questions from here? So I was wanting to expand a bit the first question of Thaisa on how did you select? Because were they on a specific survey or they were just like...
Well, most of them, they were observed. I mean, most of them were cherry-picked, of course, because they were some of them that at the highest redshift that we knew before the James Webb. Like for example, all these, if we look at the redshift distribution, all those beyond redshift 6 or 7, they were like very high priority candidates. But we also wanted to cover the lower redshift regime, in particular the AGN and star-forming populations, in order to have like a better view of the evolution of galaxies in these epochs. So let's say we have like half of the galaxies that were selected to have like a wide sample of start forming galaxies and AGN at local redshift, at low redshifts, so between redshift 3 and 5. And then beyond redshift 6, most of them, they were like more cherry-picked, but also trying to cover like different science cases.
Cool. And the last question is, what are the sizes and maybe the masses of the clumps you mentioned? The two.
I think I haven't estimated that, the stellar masses individually. No, I don't have that.
Thanks a lot, Bruno. Let's.
Thank you.
I'm sorry I made you miss your class.
Don't worry. No, it was my bad.
Okay. Bye-bye. I'll send you the